just test this. By the way, I know lunch is very soon, so I know everybody's like impatient about it. I know. Yeah, so that's why going last is probably not the best, but I appreciate you guys staying. Okay, so let me just start. So hello everyone. So my name is Misha Rybalov, and I'm going to talk about a new way to test blockchains for their resiliency to attacks. Okay, and specifically we're going to discuss BFTune, which is a testing framework that I developed with my colleagues Yahya Hassanzadeh and Khalil Kleben, and we are from the Flow blockchain team. Okay. So let's talk about the overview. We're going to cover the motivation, or why we even developed this in the first place. Why do we need this? And then the majority of the talk will be about the architecture. We're going to jump in and we're going to talk about the architecture, specifically the four main components there: the attack orchestrator, the orchestrator network, the corrupt nodes, and the local BFT test network. Okay, so let's start with the motivation. Okay, Flow is evolving into a fully permissionless chain. And what that means is right now, less than 1/3 of all 114 consensus nodes are owned by and operated by Dapper Labs, which is the company that created Flow. Smart contract deployment is permissionless right now, and we have started opening up access nodes so that anyone can become an access node operator. That's in progress right now. Okay. What we're doing is we're kind of rolling out decentralization in stages. And right now, as I mentioned, we have access nodes, but then we're planning to roll out verification nodes, and then we're planning to roll out execution nodes, and then consensus nodes. We have different types of nodes in our environment. However, as we roll this out, we are going to be at increasing risk of attacks from malicious nodes. Okay, so we want to be decentralized, but then of course we kind of make ourselves more at risk to attacks. So we need the chain to be Byzantine Fault Tolerant, or BFT tolerant. And what does that actually mean? It means up to 1/3 of the nodes can fail or be malicious, and the network can still function properly. Okay, that's our goal. So we know what we want, but how do we test for this? We need to test for BFT compliance. How do we test this? Okay, well, there's a couple of approaches that we can take. One is traditional unit testing, and I just put the picture there. This is like a toy airplane, or this is like learning to be a pilot by using a toy airplane. Like, it's fine, I guess, at the beginning, right? But it can get a little complicated very quickly, and so it might not be enough. And then it's simple to test because you have like your component. It's very simple to test, and it's isolated, so it's very nice when you do a unit test. You can mock out other components. You don't have to worry about all the other things that a full blockchain has. You can just mock it out. It's great, but it's not realistic, right? So it's easy, but not very realistic in a testing scenario. And also, we want to model different types of attacks where you could have multiple colluding nodes that are working together to create an attack. It's very hard to model that in a simple unit test. So I would say the unit test is a necessary but insufficient condition to do the testing. We definitely believe in unit tests. We have lots of them, but we needed something more than just unit tests. So we decided to create a BFT testing framework that gives us a much bigger way of testing many different attack scenarios. We want to ensure that what we deploy in production is actually what we tested, not a very simplified, mocked out version. So the way that I kind of make the analogy here, it's like having a production blockchain is like a commercial airplane. You know, there's hundreds of knobs and hundreds of dials, and and they all have to be configured very carefully to have a safe and efficient flight. Okay, and that's what we're dealing with here. So what we need to create a production environment for BFT testing. We want to be able to bring it up. We want to be able to bring it down. We want to have it in our continuous integration or CI environment, so that every time anytime anybody makes a commit, we can run the tests and properly test it. So we also want to model many nodes colluding together to create a coordinated attack. That also needs to be supported. And we also want to model different types of attacks. We want to model protocol level attacks, so like execution forks, consensus, double voting. We want to model network attacks such as spamming. So it needs to support many different types of attacks. So with that motivation out of the way, let's just jump into the architecture. Okay, this is the main figure from our paper. I'm going to go into other details of here, but just from a very high level, there's an attack orchestrator right here, and it's coordinating all the attacks. It's sort of like the master running the whole thing. There's an orchestrator network right here. We'll get into that. There's corrupt nodes, which are these two here, and then there's the local BFT test network, which is the whole box here. And we're going to go into each of those components. So let's start with the attack orchestrator. Okay, that's that red box. So this is like the analogy here is kind of like the puppet master. It's the one that's controlling, it's pulling all the strings, it's the mastermind behind the whole attack. It's manipulating a corrupt node's behavior by controlling incoming and outgoing messages. And it has, it's a centralized controller, and it coordinates the whole attack. And it also does it with multiple nodes, so it's connected to both of these corrupt nodes. The honest nodes have no connection to that, and the attack orchestrator, it also can say what kind of a network it wants to create. So in this case, there's 3 honest nodes, 2 corrupt nodes, but it could specify any kind of configuration that it wants, number of corrupt and honest nodes. It dictates what messages to send between the nodes, and there's also an interface that I'm going to show you the code for it. We have a predefined interface. So the attack orchestrator. I'm going to just give you a quick analogy. This is like a sensor or a parent that has installed a parental control software on their child's device. Okay, they can. It gives them full control over the device. They can see what's going on there. They can kind of manipulate the device. That's kind of what the role is of the attack orchestrator, and because it intercepts all the messages. Now, when it intercepts a message, it can do one of 3 things. Here, it can just act normally as if everything is fine. There's no attack. It's honest. It just passes the message through as if everything is fine. Here, it could corrupt the message. So it can change the message contents. It could change the recipient. It could duplicate the message, for instance, in a double vote. So it can do that as well. Now, just a quick caveat, it can only do that for outgoing messages because it can't alter the message for an incoming message because that would fail signature verification. And then finally, it can discard or throw away the message. Right? It can basically say it's as if the message was never sent by a corrupt node, or it's as if the message was never received to a corrupt node. Okay, so it can basically do one of these 3 things. So here's the interface for the attack orchestrator. This is in Go, and this interface is called every time a new message is coming in, whether it's an ingress or incoming message or an outgoing message. And this main interface only has 3 methods. It registers itself to the orchestrator network, and I will get into the orchestrator network later. It handles an incoming message to a corrupt node, that's handle ingress event, and it handles an outgoing message, that is an outgoing message from a corrupt node. And then it could do with that message whatever it wants. So I'm going to just very quickly give you guys just a few quick examples of attack orchestrators that we wrote, and then just the number of lines of code that it took to write them, just so you could see it was a relatively small amount to create a full attack scenario. So we have here, we have a topic validator test, and it only in about 225 lines. It can send arbitrary pub sub messages on topics that are allowed and not allowed. And what it does is it dictates some valid and invalid messages to a victim node, and then it checks that the victim node only received the valid messages. It never received the invalid messages. That proves to us that, okay, the invalid messages are getting filtered out by the network. There's another example. I'm going to try to go through these quickly. There's a gossip subsignature orchestrator in about 120 lines. It dictates valid and invalid pub sub messages with and without signatures. So it sends these valid and invalid messages and then checks that the victim only got the valid messages. And that proves, okay, that the invalid messages are not getting sent through. Finally, there's another one for Wintermute orchestrator in only 80 lines. It sends messages between several types of corrupt nodes to cause an execution fork. Okay, so we can kind of create that again in a relatively small amount of lines of code. And then the final one is a double voting one. It's not implemented yet, but we can implement it by sending two different votes, two different block proposals at the same time. We could definitely do that too. So now that we have the attack orchestrator out of the way, let's jump into the orchestrator network, which is that box underneath. This is the networking infrastructure or plumbing that's required for the attack orchestrator to send and receive messages to these corrupt nodes. It's kind of like all the stuff that beyond the actual attack itself, all the networking. It simplifies the code logic for the attack orchestrator so it can be concise and focus on the business logic of the attacks, not worry about the networking. And the orchestrator network runs a gRPC client. It connects to these corrupt nodes, which are running gRPC servers, and it uses a gRPC streaming to establish the connection. Okay, let's jump next to the corrupt nodes, which are these two here. So I'm going to just talk about these two boxes here. There's the each node, and that's every node, honest and dishonest. They have two layers. They have the protocol layer, and they have a networking layer. For the corrupt nodes, it's the exact same protocol layer as the honest nodes. And we did that on purpose because that protocol layer handles transaction processing, block creation, execution of transactions, verification of transactions, all the things that are needed to run the protocol is in that protocol layer. We chose the corrupt nodes to use the same protocol layer as the honest nodes because otherwise we would have to have different versions of this protocol layer. One is corrupt, one is honest. We didn't want to do that. We just made them all the same, and we let the attack orchestrator figure out when to be honest, when to be corrupt. That was very important. And also, we also wanted these nodes to be relatively dumb. We wanted them to be, because in an attack scenario, the attacker it's not going to be attacking all the time. It'll act honestly. It'll be like, okay, I'm doing everything I'm supposed to do. Then it'll do the attack, and then it'll go back to just being honest. So it needs to kind of be honest and malicious at the same time. And it's much easier to have these nodes not worry about that and leave all that logic with the attack orchestrator. Okay, so the other thing is, okay, so now we talked about the protocol layer. So the networking layer, that's the part that's different in the corrupt nodes. We had to modify the networking layer so they could send all their messages to the attack orchestrator, all their incoming and outgoing messages. That's the only part that's different. And let's just quickly talk about how we build those nodes. So the protocol layer is the same as the honest nodes, but we use safety flags to build those corrupt nodes, and those safety flags are applied at compile time, not runtime. And again, for safety reasons, we never want to make a node that's honest in production. We never want to corrupt it at runtime. So before it ever goes anywhere, we already put in the safety flags on the corrupt nodes. Also, the other safety feature is it only runs on the test chain, that BFT testnet. It can only run on that chain. It can't just run on mainnet or any other chain. So we kind of put that safety factor in there. Okay, now that we've covered those three components, let's just move on to the last one, which is the local BFT test network. That is, I put the sandbox image there because I just want to convey that you can create a very intricate attack scenario, but in a very safe environment. So that local BFT test network, that is a single Docker runtime that hosts all the honest and malicious nodes. It also has that yellow P2P communication network, which is our libp2p networking layer for the nodes to communicate with each other. And as you can see, the attack orchestrator runs outside of that. It could even run on a separate host. So Let me just do one last image here. This is just another way to show message flow. And as you can see here, the corrupt network is here running inside a Docker container, and the corrupt nodes are here. The attack orchestrator with the orchestrator network I put here as localhost. It could theoretically run on any other machine. It uses gRPC streaming to communicate with the corrupt network. And here are the messages, the outgoing and the incoming messages. So, in conclusion, I just want to say thank you very much. Flow is, just add a couple of points here. We're actively looking for researchers to implement attacks with BFTune. I wanted to kind of mention that we have a grant process as well to sponsor this work. Please reach out to me. That's my email for any questions or for further about this work or any other questions you would like to ask. This is where BFTune lives in GitHub, and this is where Flow lives in GitHub, as well as the address of Flow. And I wanted to say thank you very much for your time, and I'm open to questions.
Questions?
Yeah, it's very cool. Are there any kind of attacks that you can't perform going with the strategy of having the corrupt nodes run the honest code and just manipulating the messages? Is there any kind of class of attacks that are not possible?
So we think we've covered, I mean, maybe there are. We think we've covered the vast majority of attacks because just by manipulating the messages, I think we can simulate any kind of attack. But maybe there are, we haven't encountered so far.
Can the attack orchestrator tell the node to sign with a different key or things like that?
Well, the truth is the attack orchestrator has the keys of all the corrupt, they have the keys, so they could sign with a different key.
Okay, so you basically off-boarded the corrupt code into the
Yes,
okay.
yes, exactly. And that way that gives us full control.
Gotcha. Second question, is it written in a way that lets you adapt this for other blockchains, or is it very...
Yeah, so not yet. Not yet, but what we're actually, if you go to the BFTune, you'll actually see there. I just put like pointers because the code is really here in FlowGo, which is our main Flow chain. We want to extract the code out of FlowGo and put it into a separate kind of standalone environment, and that's what we created this for. So not yet, but that's the goal.
More questions? No. So.